We're going to start out this unit on electrostatics with a topic called Coulomb's law. And this was discovered by a guy with the last name of Coulomb. And he did so much work in the field of electricity that we actually name the charge, the units for charge, after him. So 1 Coulomb of charge. So we're going to start out just reviewing a little bit of what you should already know from chemistry. Matter is made up of atoms, and these atoms have a nucleus, and in the nucleus is where we find the protons, which are positively charged, and also neutrons that are zero charge. And orbiting around the outside of my nucleus, I have electrons, which are negatively charged. And the protons and the neutrons in the nucleus are pretty well stuck together. They're not ever going to come apart. The electrons that are orbiting around the outside, they're a lot more loosely attached. So when atoms bond together to form solids, the electrons can be tightly bound to the atom, as in covalent solids like glass. If you don't know this term covalent, that comes from chemistry. It's not so important in physics. These materials with tightly bound electrons are called insulators. So covalent means they're actually sharing the electrons, and the electrons are tightly bound into them. They're not going anywhere. So these are insulators. Examples of this would be like rubber, plastic. They mentioned glass already. All of those are insulators. So rubber, plastic, glass. That's why your cables that you plug things in with are covered in a layer of plastic on the outside. If, when atoms bond together to form solids, the electrons are free to move around, an example of this would be metals, these metals will be conductors. So the electrons can move around freely. It says it's a nearly free electron, meaning it's not just going to fly off into space, but pretty much it can move all around the other atoms through the metal. So metals make really good conductors. The subatomic particles like protons, electrons, and neutrons have properties known as charge. You should know that already from chemistry. It's the charge that's responsible for electricity and magnetism. Did you know that magnetism was due to electric charge? We're not going to get there for another 2 units, but it's coming up. Basic fact about charge. There are 2 types of charge that we call positive and negative. Those are kind of arbitrarily given to the protons and neutrons. There's no reason that a proton couldn't have been negative and an electron couldn't have been positive. The idea is that they're opposite. Charge is measured in units of coulombs, as I mentioned before. And it's abbreviated just with the letter C. So if you see 1 Coulomb of charge, that's 1 C. Oh, there it says, sorry. So that's the units of charge. And charge is represented by the letter Q, either big Q or little q. I'm not sure why C for charge. They didn't want to use C because they already had that for coulombs. But the variable that we use to represent charge is Q or Q. Another important fact about charge is that it is quantized, which is why the Q variable makes sense. This means simply that charge is like money. With money, there's a smallest unit, the cent, and any amount can be broken down into a certain number, whole number of pennies, but never a fraction of pennies. We're talking in the physical world right now. I know with electronic money on your credit card, they could potentially give you fractions of pennies. But in the real world, you can't ever get smaller than a penny, or in Bolivia, like a centavo. The very, very smallest unit possible is a unit of charge. So the smallest unit of a penny or money is a cent. So any larger amount is n number of cents, makes up however many dollars you have. So any larger amount is n number of cents. So 100 cents is $1. 1,000 cents, $10. 1,000,000 cents, you can figure it out. So just like there's a smallest number of money, there's a smallest number of charge. Unfortunately for us, it's not a nice even number, like 1 Coulomb is not the smallest unit of charge. We're going to see that in a minute. So it says, with respect to charge, the smallest unit of charge is called the elementary or fundamental charge. So the elementary charge or the fundamental charge, and this is the amount of charge on a proton or an electron. So the smallest unit of charge in terms of coulombs is 1.6 times 10 to the minus 19 coulombs. Any larger charges have to be multiples of E. So we can find out the total charge on an object by figuring out how many protons or how many electrons are contributing to that charge. So all larger charges are multiples of E, just like any amount of money is a multiple of cents. So Q is your charge, and it's measured in coulombs, and N is any integer. This is important. It has to be an integer, whole number. Can't have fractions of electrons or fractions of protons. You don't have to have this number memorized. It is on your formula sheet, although you will probably use it so much that you will eventually have it memorized. So if we scroll down, it says, technical comment. Some of you will be aware of particles called quarks that have charges of 2e over 3 and e over 3. So e turns out to not actually be the smallest, absolute smallest charge, but it's pretty hard to separate quarks. So for the purposes of our course, we're calling e the very smallest amount of charge you can have. In this course, you will be provided with a data page that lists the masses of the subatomic particles and the fundamental charge. So the fundamental or elementary charge, E, is 1.60 times 10 to the minus 19 coulombs. And there you have the mass of the electron, proton, and neutron. Notice that the electron's mass is quite a bit smaller than the proton and the neutron's mass. The proton and neutron, their masses are almost indistinguishable. They're very, very, very close to each other. But you notice that this is to the power of negative 31 for the electron, and these are both negative 27. So that is a difference of a 10 to the minus 4, or 10,000 times as small. So the electron is much, much, much smaller than your proton and neutron. Example number 2. The data page does not explicitly list the charges of particles. So you will need to remember the following. The electron has a charge of negative E, or negative 1.6 times 10 to the minus 19 coulombs. A proton has a charge of positive E, or positive 1.6 times 10 to the minus 19 coulombs. And a neutron has a charge of, surprise, neutral 0 coulombs. So you need to remember just that electron is negative E, a proton is a positive elementary charge, and a neutron has 0. Nothing at all. Although this does not necessarily need to be memorized, you should be aware from chemistry that an alpha particle is a helium nucleus which contains 2 protons, B+, 2 neutrons, and no electrons. We're talking about just the helium nucleus, so there are no electrons in the nucleus. What would be the charge then on this particle? Well, here's our first chance to use our new formula. We're looking for charge, given we know we have 2 protons, 2 neutrons, and no electrons. So charge is given by the formula Q equals N times the number of elementary charges. 2 protons, that'll be 2 elementary charges. N neutrons, no elementary charges. 0 electrons, well, there's no charge there at all because there's 0 of them. So this means my Q is going to be 2 times, proton is positive, so 1.6 times 10 to the minus 19 coulombs, which hopefully you can even do that in your head. Final answer is going to be 3.2 times 10 to the minus 19 coulombs. So a helium nucleus has a total charge of 3.2 times 10 to the minus 19 coulombs. Now we said before that for a conductor, the electrons flow freely and easily within the conductor. In an insulator, electrons cannot flow, but the electron orbits can actually shift slightly in one direction or another. This phenomenon is known as polarization. So the electric force, the force between positive and negative, is one of our 4 fundamental forces of physics. Charges, turns out, exert forces on each other. So we're going to fill in the blanks and then draw the direction of the electric forces in each of these cases. So, like charges that have the same both positive or both negative, like charges repel. They want to get away from each other. So, looking at this drawing, this negative charged particle and this negative charged particle want to go away from each other. So they both exert a force in totally the opposite direction from each other. So this one gets pushed up away from this one down here, and this one gets pushed down away from the one up above. Equal forces, opposite direction, kind of like your force pairs. Actually, they are your force pairs. So repelled away from each other. Well, unlike charges, one positive, one negative, they attract. Again, this should be familiar to you from chemistry. So the negative charge is going to be pulled downward towards the positive charge. It's attracted. And the positive charge is going to get pulled upward towards the negative charge, attracted. These are both the electric force. And again, equal and opposite, according to Newton's third law. Like charges repel, they want to get away from each other. Unlike charges attract, they want to get together. One of the safest places to be during a lightning storm is inside a metal car. Why is that? Well, think about what we just found out about like charges. In a lightning storm, what happens is that the lightning transports a whole bunch of electrons onto the car. But because these electrons are all negative and they're all like charges, they're going to repel each other. So because like charges repel, the electrons all gather on the outside of the car. Which means none of them go towards the middle, none of them go towards where the person is sitting. So the person inside the car is safe. So if you ever thought that cars were the best place to be because of their rubber tires, that's actually not the case. They are the best place to be because all the like charges repel each other and want to gather on the outside of the car, so the person inside the car is safe. And this is what's known as a Faraday cage. And the idea was first come up with by a guy named Michael Faraday. So take a pause in your video for a minute, in this video, and check out this video called Car Lightning from Top Gear. It's also linked in your Google Classroom assignment that shows a guy getting hit by lightning inside a car. So pause your video, go watch the Top Gear video, then come back. Pretty cool, right? Did you think it would work? Were you afraid he was going to get fried? Guess if it turns out that it's on YouTube, he probably turned out okay. Let's keep going as we learn more about positive and negative charges. Here is another example. A negative rod is brought close to an insulating ball. So this is going to be scenario number 1. Negative rod. This is my rod, has lots of negative charges on it. Also, nothing is totally negative, so it also has a few protons, positive charges, but it has way more negative charges than positive charges, is brought close to a neutral ball. So at the beginning, I have my charges distributed evenly in my ball. The ball is, because I brought them close together, is first attracted and then repelled by the rod. So first thing, we just bring it close by. First, it's going to be attracted by the rod. And then later on, this is going to be frame number 4, it gets repelled by the rod. So, why is that the case? Well, as I bring the ball close, this guy has all these negative charges in him. This one was evenly charged. The positive charges are not free to move, but the negative charges actually can redistribute themselves a bit. So they all run away, they're repelled by the electrons by the negative charge of the rod, which means the positive charge on the ball is what's close to the rod and they get attracted together. But when they actually come into contact, this is stage number 3, all these negatives, some of the negatives from the rod now jump onto the ball. And the ball becomes negatively charged. So now the negative charges on the rod and the negative extra charges on the ball are going to repel each other. So there are technically fewer charges on the rod now. I know I'm not being very consistent with my negatives. And a whole bunch of negative charges on the ball. So the ball is repelled by the rod. Pretty cool, hey? Let's take a look at another example. 2 uncharged metal spheres are fixed onto supports and are touching. This is where we start. A charged negative rod is brought in close to the spheres. So they're touching each other, negative rod in close. With the rod still in place, the spheres are separated. The rod is then removed. Show by drawing how the charges are distributed in each diagram below. So my negative rod comes in close. My positive charges are not free to move in my spheres, but my negative charges are. So with the rod close, the negative charges from all of them will run away to as far away as they can get onto the second sphere. The rod is still there when this sphere is moved away. So this sphere keeps his positive charges, and this sphere has the negative charges that actually they're going to evenly distribute themselves now because they also repel each other. So this guy keeps the negative charges, and that's how we end our scenario, with this one now having extra negative charges and this one having extra positive charges. So they are going to want to come together. They're going to attract each other. So just kind of interesting. This is called charging by induction, by bringing a charged object close but not actually touching. What we did up above, this is called charging by conduction, because the rod actually touched. So this is charging by conduction. This just shows you how the negative charges are free to move around and the positive charges are not. And so the fact that like charges repel each other ends up with some interesting scenarios. Enough talking theoretical, let's get to the math. I know you all want the math. The force between 2 fixed electrical charges is given by Coulomb's law. Coulomb's law, turns out, is actually a formula. So, Coulomb found that, like for gravity, electricity was an inverse square law. So if you got around to studying the force of gravity last year, it would look very similar to what we're going to see for the electric force. So the electric force is K, which is a universal constant, which turns out is 9 times 10 to the 9. This is true everywhere in the universe, no matter where you are, the Earth, the Moon, the middle of the Sun. The universal constant for the electric force is 9 times 10 to the 9, times whatever your first charge is, times whatever your second charge is, divided by the distance squared between the charges. And we always count this distance squared from the center of each charge. So if I have 2 charges, here's the center of one charge, here's the center of the other charge. R is going to be the distance between their centers. There's my R. So I'll say this is Q1, this one has Q2, and they have a force between them. Depending on if the forces or the charges are the same, depends on whether they're attracted to each other or repelled from each other. So to find the direction of the force, we use the rule like charges repel and opposite charges attract. So in this case, whether this force turns out to be positive or negative, we're actually going to ignore. We're more interested on whether the charges are the same, then they're going to attract each other, repel each other. If they're different, they're going to attract each other. Time for another video pause. Don't worry, it's just electrostatic discharge. In this video, there's a programmer who's going to be playing around with a electrostatic board. This is what happens in static electricity when you've rubbed your feet on carpet and then you touch a doorknob, or when you get out of a car. Sometimes you feel an electrostatic shock. When you get off a trampoline, you might feel an electrostatic shock. So go ahead and pause your video now. Take a look at the video. Don't worry, it's just ESD. Alright, before we get into the actual math of this thing, we're going to look at an example that just has to do with vectors. I know you all love vectors. We're thinking about the direction of the electrical force on a certain charge distribution. So, although we saw up above from our diagrams that each charge is going to experience a force, we're going to ignore the forces on all the charges except the plus Q charge. We only really care about what happens to this guy because of these other three charges. And we're only concerned with the direction. We're going to find magnitude maybe later on. So find the direction of the electrical force on the plus Q charge. Well, let's call these charge A, charge B, and charge C, and think about what direction each of these would go and which ones are going to be bigger or smaller. So between our friendly charge, our focus charge, and charge A, we have plus Q on our charge and negative 2Q on A. So are they going to be attracted or repelled? That's right, they're going to be attracted. And will that attraction push or pull charge Q to the left or to the right? Okay, so hopefully you can see that it will pull him towards the right. And I'm going to call this force from charge A. Between charge Q and charge B, they are the same, both positive, so they're going to be attracted or repelled. Well, like charges repel, which means charge Q is going to be pushed or pulled towards charge B. Well, like charges repel, so it's going to be pushed away from charge B. It's going to go up in this direction. And because charge B is farther away than charge A, so charge B is farther away than charge A, it's going to be a smaller arrow. So it is going to be up at an angle away, but it's going to be a smaller arrow than FA. So there's FB. And then between charge Q and charge C, again plus and minus. So opposite charges, they attract or repel. They attract, which means charge C is going to be pulled downward. Sorry, not charge C. Charge Q is going to be pulled downward towards charge C. And I might make this arrow just slightly bigger than FA because it looks like the distance is slightly less than between A and Q. So this is FC. So if I want to find the net direction, I need to add all these vectors together and I need to add them tip to tail. So I'm going to take FA and redraw it over here. That looks about the same. From the tip of that one, I'm going to try to draw FB. Looks something like that. Here's FA, FB, and to finish off, I'm going to draw FC from the tip again, slightly longer than FA. My resultant direction is from start to finish, so I started drawing here, and I finished drawing here, so I'm going to connect those two. There's the direction. This is the F net. So it's kind of in the southeast direction. But that's all we're looking for, is a diagram that's approximately in the right direction. There's my F net. All right, let's keep going. So to solve problems like this, in general, We need to make sure the charges are expressed in charges of coulombs. And a lot of these you're going to see things like microcoulombs or millicoulombs. Remember that micro means 10 to the minus 6, so this is 10 to the minus 6 coulombs. Milli is 10 to the minus 3. That's also on your formula sheet. So I can easily change from microcoulombs to coulombs just by adding this multiplication factor. Then we're going to substitute the charges and distances into the Coulomb's law to find how big the force is. And again, Coulomb's law, F equals K Q1 Q2 over R squared. And then we're going to use the concept of like repel, unlike attract to find the direction of the force, just like we did for example number 7. So it's kind of a 3-step process. Steps 2 and 3 are more involved than step 1. Technical comment. If we have unlike charges, for instance, Q is negative and little q is positive, then the answer we get for the force will be negative if you plug in the negatives. A negative times a positive is a negative. So positive and negative forces is going to give me a negative force. But the significance of the negative is actually to indicate attraction. So if you're plugging negatives into this formula, it means they are being attracted. So we should not consider that the force is negative, because usually a negative force means left or down or west. In other words, we drop the negative when stating our answer. We don't include a negative as part of our force answer. Neither should we interpret the negative as being left, down, west. It just means attraction. But the attraction could pull to the left, could pull to the right. So basically, the negative is not needed. And I would go so far as to say, don't include it. It's just going to confuse you. So, some people write Coulomb's law as being using an absolute value. F is K, absolute value of QQ over R squared. So that we don't end up with a negative force, thinking that our force is left or down or west or any other thing that you can think of that negative might mean. So drop the negatives when you're putting charges into your force equation. And here's our first example. Example number 8. Find the electrostatic force on a helium plus ion, which has a radius of 2 times 10 to the negative 11 meters. So helium plus ion. And they've given us a nice diagram to show us that in the nucleus of our helium atom, we have 2 protons. And orbiting around the helium plus ion is only 1 electron. So we want to find the force between these 2 protons and this 1 electron. So in this case, we can go straight to our formula. It might help you, again, if you're still thinking this through, to use our old DFIC acronym, which was write down your data. So maybe that helps us. Data, I have K is 9 times 10 to the 9 always. The big Q, well, I could use the 2 protons, so this is going to be 2 times 1.6 times 10 to the minus 19. And the little q is going to be my electron is just 1, so it's a negative 1.6 times 10 to the minus 19, only 1 electron. And the radius, the distance between them, is 2 times 10 to the negative 11 meters. If you don't need to write these down, no worries, you don't have to, but maybe it helps you organize yourself a little bit. So my formula, F is K Q Q over R squared. And you can use Q1 and Q2 instead of big Q and little q. I just find it kind of nice not to have to write subscripts all the time. So I'm going to plug in my data insert, so 9 times 10 to the 9, 3.2 times 10 to the minus 19, 1.6 times 10 to the minus 19. I'm going to drop the negative because I don't want it included in my answer, divided by 2 times 10 to the negative 11. All squared. Let me pull out my handy dandy calculator. There we have it. And plug that in. So 9E9 times 3.2E negative 19 times 1.6E negative 19 divided by, I'm going to put this in parentheses because I'm going to square it, 2E negative 11 close parentheses squared. And that gives me a force, a pretty small force, I might say, of 1.15 times 10 to the minus 6 newtons. Force is still measured in newtons, just like always. And I'm going to round this to 3 sig figs. If you wanted to round it to 2, it would be 1.2 times 10 to the minus 15 newtons. That would also be fine as an answer. So there's your final answer. Make sure you are showing your work minimum. You need to show this insert step. If you don't want to write the formula down, that's fine. I know you have it on your formula sheet, but you do need to show this insert, not just plug it into your calculator. All right, now that we got that, we're going to move on. It says, although the force you calculated, this seems awfully small, but we should note that we are dealing with electrons, which have a very, very, very small mass, 10 to the minus 31. So if we were to find the acceleration of the electron, this acceleration of the electron in the example above, we would use this formula. This is F equals ma. So F net equals ma. If my net force is this 1.1, I'm going to not round it yet when I plug it back in again. So 1.152 times 10 to the minus 6 is my force. The mass of my electron, 9.11 times 10 to the minus 31. Let's see what that gives me. So I can just hit divide to keep my second answer. Divide by 9.11 E. Whoops. Shift answer. 9.11 E negative 31. Going to be tiny. This gives me an acceleration, a whopping acceleration of 1.26 times 10 to the 24 meters per second squared. That is huge. So on the atomic scale, 1.15 times 10 to the negative 6 newtons is actually a pretty big force. So we see it's huge in atomic terms. Let's keep going. A few more things to take a look at. Example number 9. Where are we? Here we are. Find the net electric force and direction on the positive 1 microcoulomb charge below. So we are interested in the positive 1 microcoulomb charge below. And we need to make sure that when we're plugging things in, everything is base units. So microcoulombs means 10 to the minus 6 coulombs. So 1 microcoulomb is 1 times 10 to the minus 6 coulombs. So this would be negative 2 times 10 to the minus 6, 1 times 10 to the minus 6, 1 times 10 to the minus 6. And if you remember centimeters, centi is 10 to the minus 2. So 20 centimeters is 20 times 10 to the minus 2 meters. 10 centimeters is 10 times 10 to the minus 2 meters. If you wanted to actually do that multiplication, you could. This would be 0.2 meters and 0.1 meters. Or if you want to type it in just using this multiplication factor, that also will get you the right answer. So no worries either way that you want to do it. So we want to find the net electric force and direction on this middle charge below. So like we did in the diagram with the rectangle of charges above, we need to consider what direction each of these other charges will push or pull the 1 microcoulomb charge. And then we're going to add those as vectors. So a negative 1 microcoulomb charge, let's call this charge A, and this one charge B. So if we think about our 3 steps that were written up above, first step was to make sure we were in base units or using coulombs, in this case also meters. Step 2 was to calculate the force between A and star and between B and star. So I'm going to call this FA, K, QA, Q star over R squared, where R is the distance between A and star. So maybe I'll call this RA. And I'm also going to need to calculate FB, which is going to be K, QB, Q star, over the distance between B and star. I'm just going to call that RB squared. So this is RA, and this is RB. So go ahead and pause your video for a minute. Go ahead and show your insert. So insert your numbers into the formula, and go ahead and find out your answer, then come back. So pause your video, try it for yourself, then come back. All right, so we plug in all our numbers. Notice that I didn't plug in any negatives into my formula because I want my force to be positive. And you can either plug this in as 20 times 10 to the minus 2, or as, in this case, this one over here is 0.1. So I get force A on star being 0.225 and force B on star being 1.8. Now to find the direction, I go back and think about like charges repel, opposite charges attract. So between A and star, these are opposite charges. They're going to attract. And so what that does to star is it pulls it towards A. So there's my FA. Opposite charges attract. So again, what that does to star between the 1 and the negative 2 microcoulombs is it pulls it towards B. And as we saw from our calculations, FB is a whole lot bigger than FA. So here's my FB. And to find the net force, remember, if two forces are in opposite directions, I'm actually going to just subtract their numbers. So they're pulling in opposite directions, so my net force is 1.8 minus 0.225. 1.8 minus 0.225. And I'm going to round that to 3 sig figs. So my net force, 1.58 newtons. And the direction is determined by the bigger force. So my bigger force in this case is to the right or to the east. You can use either of those. I'm going to use right and left, but you could use east if you wanted to. And that would be my final answered. Oops, I'm going to put a vector arrow over my Fnet. So include direction, include magnitude. So far so good. Let's keep going. Example number 10. This is a bit more of a theoretical question. You're in grade 12 now. You're going to see a few more of these. At which point, approximately, could we place a positive 1 microcoulomb charge so that it would experience no net electrical force? And they give us a couple options. Here at point A, here at point B, here at point C, here at point D, and here at point E. And we're thinking, okay, where can I put my plus 1 microcoulomb charge so that there's no net electrical force? This means the forces balance each other. Equal in magnitude, opposite in direction. This should be magnitude. There we go, that's better. So when I think about putting my 1 microcoulomb charge here, positive 1 microcoulomb charge is going to be attracted to the negative 1 microcoulomb charge. So what my first force is going to be to the right. And it's also going to be attracted to the negative 2 microcoulomb charge. So I don't know how big these arrows are because this one's a lot farther away. So I'm guessing that the second arrow is actually going to be smaller. But they're both pulling the same direction. So this is never going to give us a no net electrical force. They're going to add together to give us a bigger force together. If I consider then actually thinking about what happens if we go all the way to the other side, this is going to be exactly the same scenario. Over here, it's going to be attracted to the negative 2, it's going to be attracted to the negative 1, so both my force arrows would still be in the same direction, so point E is never going to work either. So now I'm left with 3 options. If I think about point C up here, again, attracted towards this one, attracted towards this one, they're not equal in magnitude and opposite direction. It's hard to tell if they're equal in magnitude, but they're certainly not opposite in direction. So that leaves me with 2 options, B or D. And this is where I start to think about a little bit about this equation, F equals KQQ over R squared. As a charge gets bigger, it's going to exert a bigger force. The bigger the charge, the more force we get. But as I get farther away, the smaller the force gets. So if I think about point B, it's really close to this one, but this one has a bigger charge. So it's possible that those differences would cancel each other out because I'm going to be attracted this way towards this charge, attracted this way towards this charge. So it's possible spot B looks like my best option at this point. If I look at point D, well, I'm farther away from this one, and it's also the weaker charge, which means this direction is going to be a whole lot stronger attraction than this direction. So looks like letter B is my answer. So justify your answer by drawing the force vector arrows at each point. Check. That's what we did. So not all of these questions involve direct multiplication or manipulation of numbers, although you do need to keep the formulas in mind to know which of these 2 points was the most likely after you thought about the attraction and repulsion of each of the other options. Example number 11, this is the last one. Find the electrical force, including direction, on the electron shown below. So this is what we're looking for. And we want to know what direction, how hard is the force going to pull from each of these other charges in the diagram. So pause your video now and take a minute to see if you can figure it out. Remember that you need to express all your charges in coulombs, so change these microcoulombs. Watch out for the micrometers. You also need to change those into meters. And then find your forces and add them as vectors. Then come back and we'll walk through the solution. Alright, so I went ahead and calculated the forces for charge A and charge B. Let's think about the direction that they're going to push or pull the electron. So remember that an electron is negatively charged, and so that negative charge is going to be repelled from the other negative charge. So my force A is going to be to the left, pushing it away. So maybe I'll just add that on here. So this is 7.2 times 10 to the minus 4 left. And my negative electron is going to be attracted to my positive 1 microcoulomb charge. It's going to be attracted downward, and that force vector is about half the size. So if I want to find the magnitude and direction of the net force, I need to add these 2 as vectors. Fortunately for you and for me, this is a right angle triangle. So I'm going to redraw force A going this way, then tip to tail, force B. Remember, always tip to tail. That's why your vector arrows are important, what direction that they're going. Here's my FB. And my net vector is then going to be from start to finish the hypotenuse. So if you didn't finish this yet, maybe pause your video at this point and see if you can figure out F net. You need both the hypotenuse magnitude using a squared plus b squared equals c squared, and you should find this angle theta using SOHCAHTOA. So if you haven't done so already, pause your video, otherwise I'm just going to keep going. So F net then is going to be the square root of 7.2 times 10 to the minus 4 squared plus 3.6 times 10 to the minus 4 squared. Here we go. Remember that it depends on your calculator how many exponents you're going to need in order to get this to come out correctly. But I think for my calculator, yep, this is enough. So on the Casio, that's what we got. F net equals 8.05 to 3 sig figs, or 8.0 to 2 sig figs, times 10 to the minus 4 newtons. And I'm going to use tangent to get me my angle. So FB is the 3.6, and FA is my adjacent, opposite over adjacent, 7.2. Take the inverse tangent of that, and my actually 10 to the minus 4s, they're just going to cancel out altogether. So I'm going to take the inverse tangent of 3.6 over 7.2. And this is giving me an answer in radian mode. For physics, I need my answer in degree mode, so I'm going to go down to change into degree mode. That again, and that tells me theta is 26.6 degrees. I'm just going to add this onto right here, 26.6 degrees. And looking at this diagram, that's going to be south of west. So full final answer. There you have it. So when you're solving these kind of electrical force type questions, first calculate the force between each of the charges and the charge that you're focusing on. Then figure out the direction that they're going based on your diagram. Add them as vectors, which may take Pythagoras, SOHCAHTOA, maybe even sine law and cosine law occasionally. And give your final answer, including a direction. All right, now it's up to you. Have fun.